Welcome back, learners. In previous part we had discussed about the chemistry of furans, and also we have learned their different methods. How can we synthesize the furan from different methods? In this part we will discuss another very important method for the synthesis of furan and thiophene, Pahl-Knorr synthesis, and along with that we have to discuss here different synthesis or different methods of preparation of thiophene. So this is the Pahl-Knorr synthesis, and it is very important synthesis for the preparation of pyrrole, furan and thiophene. And in this synthesis we have to use 1,4-diketone. So the 1,4-diketone converted into pyrrole, furan and thiophene. So it is synthetically valuable method. This Pahl-Knorr synthesis, this method is a valuable method, and it is invented by German chemist Karl Pahl and Knorr in 1884, adopted as a method for the synthesis of furan, pyrrole and thiophene. And in this, the characteristic of this synthesis, ring formation takes place. So this is the main characteristic of this synthesis, Pahl-Knorr synthesis. So 1,4-diketone convert into a ring. So ring formation takes place during the reactions. So you will see here, this is a 1,4-diketones. So this 1,4-diketone, in presence of acid catalyst, we get a cyclic compound, that is a furan derivatives. So the protonation of one carbonyl, the carbon number 1 which is having a carbonyl oxygen, at that carbonyl oxygen protonation takes place. After protonation, then dehydration, then we get a ring formation, acetyl ring formation, that convert into furans. So this is very important method. We will discuss mechanism also. And learner, on your screen you can see a very important fissile microwave mediated transformation method. So it is a microwave mediated reactions, and it is a one pot reaction, and only 4-5 minutes takes. This reaction is completed only 4-5 minutes. So that is the one pot synthesis. And what is happening here? The transformation of a 2-butene 1,4-diones and 2 butynes 1,4-diones converted into furan derivatives. So you can go, if you want to go the details, there is a reference mentioned over here. So it is a microwave mediated transformation of 2-butene 1,4-diones and 2-butyne 1,4-diones, we get a furan derivatives. Another Pahl-Knorr synthesis which is used for the synthesis of pyrrole. So the difference is that in furan synthesis we have to use acid catalyst, but for the synthesis of pyrrole we will use here primary amine. So 1,4-diketones in presence of primary amines converted into pyrrole derivatives. Similarly, for the synthesis of thiophene we have to use phosphorus pentasulfide. So that phosphorus pentasulfide act as a catalyst, and that 1,4-diode converted into thiophene derivative. So this is a Pahl-Knorr synthesis. So Pahl-Knorr synthesis is a synthetic valuable method for the preparation of, for the synthesis of pyrrole, furan and thiophene. Now we will discuss here the synthesis of that furan. So in this synthesis, all the dicarbonyls converted into corresponding heterocyclic compounds, and the reaction is carried out in the aqueous acidic condition. And here we will use the protic acid such as sulfuric acid, hydrochloric acid, or also we can use anhydrous conditions, and in anhydrous condition we will use Lewis acid, or also we can use dehydrating agents. So the dehydrating agent can be phosphorus pentoxide, anhydrides or zinc chlorides. So these are the dehydrating agents we can use in the synthesis of furan or in Pahl-Knorr synthesis. Now it is the mechanism. So on your screen you can see the mechanism. So here 1,4-diketones. So you can see here 1,4-diketone abstract a proton from the acid, because the reaction takes place in acidic medium. So abstraction of a proton from the acid at 1 carbonyl oxygen, and we get a enol of other carbonyl group. Now after that dehydration, and after dehydration it converted into hemiacetal structure, and that hemiacetal removal of a molecule of water after dehydration, finally we get a furan derivative. So this is the mechanism of a Pal-Knorr synthesis of by which we can synthesize furan. Another very important synthesis is cyclization of alkynes. So here it is a photochemical reactions. It means the reaction takes place in presence of UV light or light. This is the alkynes. Alkynes abstract a photon from the light, and the reaction of alkynic ketone in alcohol. After that, abstraction of a alpha hydrogen from the alcohol by excited carbonyl oxygen, cyclization. After cyclization we get a furan derivatives. So this is a cyclization of alkynes. And another very important method is a ring expansion. How we can get the furan from a small ring. So this is another very important method. So on your screen you can see a 3-member ring. So 3-member ring can be expanded to the 4-member rings. So ring expansion of alkynic oxime with acid H2SO4 or HgSO4. When this abstract in presence of mercuric sulfate or H2SO4 sulfuric acid, ring opening takes place. That is the 3-member ring, epoxide ring open, and after that ring open we get a diol. So after ring opening of we get a diol, then diol convert into furan. So this 3-member ring is converted into 5-member ring. So it is a expansion of is 3-member ring to 5-member ring, which is a furan we are getting over here. Similarly on your screen this is a 4-member rings. So the 4-member rings converted into 5-membered furan derivatives. The reaction takes place in presence of BF3 and diethyl ether. After that we get a carbonium ion, and that carbonium ion is here. Again the expansion of ring takes place. The 4-member ring is converted, you can see on your screen, ring opening then ring closing. So ring opening we get a carbocation. That carbocation, the carbon is joined with the oxygen, with the carbon, other carbon, and we can get here a 5-membered ring. So that carbocation is make a bond with oxygen. So ring expansion and furan tetrahydrofuran. In this structure we are getting THFF. So it is a derivative of furan. Similarly, transformation of 5-membered tetracycles. So this is 5-membered tetracycles to 5-membered, but the difference is that 5-membered ring having 2 heteroatoms. On your screen you can see here this is a oxazoles. Oxazoles having 1 nitrogen atom and 1 oxygen atom. So this oxazole react with alkyne, 4 plus 2 deals, aldehyde reaction takes place, cycloaddition takes place here, C3 and C4 here react with and to form a furan derivatives. So this is the expansion of 5-membered ring to again 5-membered ring. So but there is a 5-membered ring is having nitrogen atom. So that removal of that nitrogen atom as a RCN, we get a furan derivatives. Again very important method is a ring contraction. The previous method was ring expansion and it is the ring contraction. How the 6-membered ring contract to the 5-membered ring? So it is a oxidative ring contraction of pyrrolium salts. So here ring contraction with aqueous hydroperoxide, we get a 2-acyl furans, and on acid catalyzed degradation we get opening of chain takes place, then again we get a oxocation. That oxocation is contract into furan derivative. So, it is a ring contraction method. Similarly, here formation of furan on heating of food. As I told you, the packed food when on thermal degradation convert into furan, it gives the furan. The reason is that the food contain amino acids. So, that amino acid can be serine, cysteine, alanine or aspartic acids, and that convert into that PUFA and carotenoic acid. Along that carotenoic acid on heating convert into furans. So, this is the reference. If you want to go to detail, you can see the reference how that packed food on thermal degradation give the furans. Similarly, these are the another important reactions, how the furan and methyl furan which is present in the food, which are highly volatile. So, during the traditional cooking, wide range of compounds are formed which is present in selected food. So, there is also reference, you can go into the details, and these are the compounds derivatives of furans and methyl furans which can be found in the foods. Now, another important topic we will discuss here, chemistry of thiophenes. What is thiophenes? As I told you, thiophenes are also heterocyclic organic compounds which contain sulfur atom. So, it is having sulfur atom, 5-membered heterocyclic compound. The molecular formula is C4H4S. It is colorless liquid, density is 1.051 grams per milliliter, melting point is 0.38 degrees Celsius, boiling point is 84 degrees Celsius, and it is insoluble in water and miscible with organic solvents. But learners, if we compare the reactivity of this thiophene, it is 300 times more reactive than benzene. As I told you in the previous lecture, the aromaticity is based on the electronegativity. So, it is the least electronegative atom. The sulfur is the least electronegative atom. So, it is the most aromatic, and the reactivity is proportional to the half of the stability. If the stability is more, the reactivity is less. So, here thiophene is monocyclic heteroarene. Thiophene is also natural product found in coffee arabica. Thiophene and its substituted derivatives shows important application in medicinal chemistry. So, these are the thiophene derivatives. On your screen you can see thiophene derivatives act as a anti-inflammatory agent, and other number 5 agent, the derivative is used in treatment of disease, and these are also polysubstituted thiophene derivatives which can act as an anti-cancer and antimicrobial activity. So, these are the thiophene derivatives and have a very important medicinal values. Along with, you can see on your screen, these are the again different thiophene derivatives. All the structures on your screen you can see, these are having a thiophene. So, these thiophene based compounds has potential anti-inflammatory activities and very useful in medicinal chemistry. And again here these are the 6 electrons. If you compare these thiophene structures, thiophene is also having 6 electron, it is also planar, it is also cyclic, having conjugated system, but it is the less reactive than furan and pyrrole. So, the reactivity order is pyrrole, furan and thiophene. Thiophene is least reactive, but it is the most aromatic in nature. Why most aromatic in nature? Because the electronegativity of thiophene is less, that it is the least electronegative atom. So, it means that if any atom is least electronegative tendency, it will be hold the electron very less. Here the affinity of, or we can say the ease of electrons in delocalization is more due to the less electronegativity. So if the ease of delocalization in that ring is more, it will be most aromatic. Again, this is the 7. Here you can see on your screen, this is also thiophene, and it is the biotin. This is also called vitamin H, and learner, on your screen you can see the structure. This biotin H, this biotin or vitamin H is naturally occurring thiophene, and it is very important derivative for energy production in our biological system. And these are the some foods which contain vitamin H, and it helps to support a number of enzyme or enzymatic reactions present in fruits and vegetables. So these are the some important foods which contain vitamin H. Learners, now synthesis of thiophenes. How can we synthesize the thiophene? One important method is intramolecular cyclization. So here in this method, this is the structure, you can see this is the reaction. On your screen you can see the reaction. Cis-4 aryl alkyne thiocrotonitriles. So this is the thiocrotonitriles. This thiocrotonitriles in presence of acid catalyst and dry ether convert into 2-amino thiophene, and intramolecular attack of protonated nitrate on the sulfide sulfur takes place, and formation of sulfonium ion as an intermediate. So that sulfonium ions converted into thiophenes. So it is a derivative of thiophene. So this is intramolecular cyclization of cis-4 aryl alkyl thiocrotonitriles. So here attack of chloride ion to give 2-amino thiophene and removal of aryl alkyl crotonitriles, and we get that thiophene derivatives. Another important method, that is a industrial methods. So industrial method is from the hydrocarbon. So you can see on your screen, this is a butane, it is a hydrocarbon. So the from butane we can get thiophene. So butane in presence of sulfur, cyclization of butane with sulfur at high temperature, we get thiophene, and as a side product we get H2S. So H2S is slightly toxic gas. Now this is another method, butane and butadiene. Derivatives of butane also on dehydration convert into thiophene derivatives. So here aromatization takes place, and in presence of sulfur, that is the 1,4-butadiene derivative, chlorobutadiene. So that chlorobutadiene or that 2-methyl-butadiene on dehydrogenation with sulfur, interaction with alkenes by adding of that sulfur, further dehydrogenation which leads to aromatization, and that aromatization we get a aromatic ring which contain 5 atoms, 4 carbon and 1 sulfur. So these are the methods which we through which can get thiophene derivatives. So this is another important method, mixture of acetylene and hydrogen sulfide. So when acetylene is passed over the hydrogen sulfide gas, we have to pass that reaction through a tube which containing alumina, and the reaction takes place at 400 degrees Celsius temperature. So this is also industrial method. So we get a thiophene. Another important method, mixture of sodium succinate and phosphorus trisulfide. When sodium succinate and phosphorus trisulfide heated at 200 degrees Celsius temperature, we get a thiophene. So, this is also another important industrial methods. Now, here we have to discuss Hinsberg synthesis, how we can obtain the thiophene through Hinsberg synthesis. So, it is a name reaction which is invented by the Hinsbergs. So, here in this reaction, alpha diketone plus dimethylene sulfide gives converted into thiophene or thiophene derivatives. So, we will see here we will discuss the reactions. So, thiophene, this is diketone. On your screen you can see the diketone, and this diketone react with thiophene carboxylic acid. So, here we can carboxylic acid or esters or acid derivatives. So, acid derivatives you can see on your screen, there is a ester. So, when this thiophene carboxylic acid derivatives which is having ester group react with diketone to form alpha diketone, and along with that thioacetates. So, this is the thioacetate and alpha diketones convert into thiophene derivatives. It is very important reactions. Now, we will see how the mechanism takes place. Hinsberg methods, how the reaction takes place. So, that alpha diketone and the carboxylic acid derivatives which contain thiophene, which contain sulfur. In this reaction, condensation of alpha diketones with dimethylene sulfur which containing compounds which contain sulfur. So, here electron withdrawing groups present over here like COR or cyanide group, intermediate which formed over here alpha, this is gamma lactones, and the reaction takes place in presence of sodium or potassium alkoxides. So, we get a thiophene derivatives. So, here in this reaction you can see condensation of 1,2 diketones with thiodiacetate. The reaction takes place in presence of sodium or potassium alkoxide, is called Hinsberg method. So, you just remember what is the Hinsberg method. In Hinsberg method is a condensation reaction. The reaction takes place with 1,2 diketones and thiodiacetate in presence of sodium or potassium alkoxide, and the intermediate form is lactones. So, this is the Hinsberg method. Next important synthesis is Gewalt synthesis. So, in Gewalt synthesis, condensation of ketones or aldehyde with alpha cyanoesters, the reaction takes place in presence of elemental sulfur. Elemental sulfur is S8 and base, and we get a polysubstituted 2-amino thiophene. So, you can see here this mechanism, you can see how the elemental sulfur react with that cyanoester and finally converted into substituted thiophene. Now, in this the reaction takes place in different parts. First is novel condensation takes place between the ketone and alpha cyanoesters to form a stable intermediate, and finally that intermediate addition of the elemental sulfur that elemental sulfur is added to the intermediate, and cyclization, tautomerization, finally converted into thiophenes. Another very important method is Furans thiophene synthesis. So, it is invented by the Furans, and it is also very important method. Here 3-hydroxythiophene dicarboxylate in presence of base convert into that thiophene derivative. It is the name reaction which allow the formation of 3-hydroxy 2-thiophene carboxylic acid derivatives, ring formation takes place, ring formation reaction, and it's a aldol type condensation. The reaction of thioglycolic acids and alpha beta acetylenic ester in presence of base takes place. So, this is a Furans Thiophene synthesis, and this is the synthesis mechanism how the reaction takes place. So, reaction is activated. Another reaction is another important synthesis, reaction of activated alkyne with alpha mercaptoketones of esters. So, here in this reaction, condensation of alkynes with alpha mercaptoketones or esters, it is a Michael type reaction, and addition of thiolate ion to the alkyne. Cyclization, after the cyclization, aromatization, we get a substituted thiophene. And here another important method is 2 plus 2 plus 1 cyclization reactions. So, here acetylene when react with sulfur, we get a tetraphenyl thiophene. So, in this reaction 2 plus 2 plus 1 cyclo addition takes place. So, it is the mechanism how the cyclization aromatization takes place, and we get a 2 plus 2 plus 1 cyclic added product over here. Another very important method is mesoionic heterocyclic dipolar negative and positive charge delocalized through. So, what is this reaction? Here 1,3-dithiolium 4-olate. In this next slide you will see the structure, 1,3-dithiolium olate and 1,3-thiazolium 4-olates leads to the formation of thiophene derivatives via intermediate and involving the cyclization. So, this is the here we can understand the how the cyclization and aromatization takes place. So, this is the another important synthesis, Pal-Knorr synthesis. As I told you in the previous part, this is in through Pal-Knorr synthesis we can synthesize furan, pyrrole and thiophenes. So, in synthesis of thiophene, condensation of 1,4-dicarbonyl compound in presence of an excess of sulfur. So, we have to use excess of sulfur phosphorus pentasulfide. This is also called Lawson's reagent. So, using that Lawson's reagent, we can get thiophene through the Pal-Knorr synthesis. So, here H2S is formed, which is a side products. So, learners, in this part we had discussed about the Pal-Knorr synthesis of formation of furan and thiophene, how the thiophene can synthesized through the 2 plus 2 plus 1 cyclization reaction, cycloaddition reactions, and why that thiophene is more aromatic if we compare to the other 5-membered heterocyclic compounds. Thank you.